What is the strongest filament type printable on consumer 3D printers? Welcome to MyTechFun. I'm still on a holiday, but I have a lot of free time, so I'm preparing this video. If you are not new on my channel, then you probably know that I have my regular testing method, and the results I'm collecting in one summary table for my Patreon supporters. And in this video, I want to analyze these results. I had more than 250 rows in that spreadsheet. And a few years ago, I did something similar, but at that time, I didn't have enough data for very important technical filaments, like PETG-CF, PPA, PPS-CF and similar, and they will be included in this video too. The grouping will be different because I noticed that ASA, ABS, they have very similar mechanical properties, so they will be considered as one group, but I will separate carbon fiber or glass fiber versus no fiber reinforced versions, because here I noticed that there are very important differences in the properties. Of course, with some groups I don't have enough data for no fiber versions, for example PET-CF, PPA, PPS-CF and similar. The evaluation will be different too, because in that video I took the strongest filament type in one specification as 100% and all others are compared to this one. But ChatGPT suggested me to take the PLA as 100% and all other values and types will be compared to this one. So let's see the presentation. And huge thanks to the Polymaker, because they are sponsoring not only this video, but the whole channel is sponsored by them. Let's start with the first graph. Here you can see the grouping and how many items are in that group. And sometimes the first half I will call as a basic materials, and the second half I will call as an engineering filaments, even if ABS, ASA could belong to both. And glass or carbon fiber filaments are in a separate group, so at the end we can learn about the effect of the fiber reinforcement too. Tensile strength. The object is printed in horizontal position with the smallest cross-section area of 4x4 mm, and I'm pulling it until the break. And for basic materials, we can see that the PLA is the strongest and ABS ASA is the weakest, even if it is reinforced with the carbon or glass fibers. From engineering materials, more or less they are very similar, but a big jump we can see with the PPA-CF, which is almost too strong for my basic crane scale. Layer adhesion. The object is printed in vertical position and also the smallest cross-section area is 4x4 mm, and I'm measuring the break load. From basic materials, PLA is the strongest and far the weakest is the ABS ASA. And usually the fiber reinforcement will make this layer adhesion weaker in most cases, except with the PETG. Looks like the company somehow solved that carbon or glass fiber reinforcement sticks good to the basic materials, and I could measure here some really good layer adhesion. And one more thing to mention, that PPA-CF, this is incredibly strong, but compared to the vertical tensile strength, which I usually compared in the videos, this looks weak. But look, if we compare this to the other materials, this is very good layer adhesion. Two-sided shear test. The object is printed in horizontal position, diameter is 5 mm, and I'm pulling until the break. From basic materials, the PLA is the strongest, but there is no big difference between them. Engineering filaments are stronger, but far the strongest is the PPA-CF. And we can see that in every case, the fiber reinforcement helps with the horizontal printed objects. Same two-sided shear test, but objects are printed in vertical position. I started this testing much later, but I have at least 50% of the measured data, so I believe that's enough for some relevant analyzing. And from the basic filaments, we can see that again ABS ASA is significantly weaker, mostly because of that weaker layer adhesion. From other technical filaments, we can see big differences, deviation, but still far the strongest is PPA-CF. Torsion test. Objects printed in horizontal position, diameter is 6 mm, and I'm measuring the load at 90-degree rotation and also the maximum load. But on the graph I present only the load at 90-degree rotation. We can see that from basic materials, again the PLA is the strongest. Other technical filaments more or less very similar, except PPA-CF, which is again very strong in this test. Same torsion test, but objects are printed in vertical position, but here it usually breaks suddenly, so I can measure only the max load. And we can see from basic materials, yes, PLA is the strongest, but the difference is not big. Again, with technical filaments, we can see some small jumps, but they are very similar to each other, except again PPA-CF extremely strong in this test. IZOD impact test. Object is soldered in vertical position. Now I'm measuring the Sharpie test 2. I'm just presenting it here, but I don't have enough data. I started with this test much later. And we can see the most important property of the ABS-ASA material. It is the toughest between all filament types. Another myth is busted here. Pay attention to these numbers. This means the PETG is more brittle compared to the PLA. Polycarbonate without fibers is the second toughest filament type, and this is maybe the only weak point of the PPA-CF. And the strongest fiber-reinforced filament in this test is the PA, polyamide, usually PA6 or PA12. 3-point bending test. Distance between supports is 50 mm, and I'm placing these loads one by one every 1 minute, and I'm measuring the deformation after 1, 30 and 60 seconds. And on this graph you can see the deformation under 5 kg after 30 seconds. And of course this is the deformation, so the smaller is better. And there are several conclusions. First is that from all no fiber reinforced filaments, the PLA is the strongest. Another conclusion, that the fibers helps in every case, no exceptions. And from all filaments, two strongest are the PPS-CF and of course PPA-CF with very minimal deformation during this test, even under 10 kg. Another bending test on my universal testing machine, which follows better the ISO 178 standard. Distance between supports is 64 mm and the supports are rounded diameter 10 mm. Now I started this test recently and I have only few measurings here, but even from that we can see that the fibers helps with the stiffness. Bending strength depends from the maximal load, and the elastic modulus, it depends from the deformation too, but every time the fibers here we can see with the ASA, ABS or with the polycarbonate helps. I believe that the differences should be very similar to this one, but I have only few measurings so far. Creeping the deformation under constant load of 1.25 kg in this case. I'm locking the position and I'm measuring the distance between two reference surfaces daily next 5 days. And here we can see the deformation after 1 day. Smaller is better, and we can see the biggest disadvantage or weak point of the PLA. If the temperature would be just a little bit bigger, let's say 35 degrees Celsius, this difference would be even bigger. From the basic materials, the second best is PETG, and then ABS-ASA. That's why this material is recommended for the Voron parts, for example. Another conclusion, that the fibers always helps here a lot. Here we can see 3 examples. Another conclusion, PA or nylon, this is PA6 and PA12, don't like constant load. It is good in other things, but it will deform under constant load. Now, PPA-CF and PPS-CF. If I place the load, the deformation with the PPA-CF is smaller. This means smaller stress. But even with that bigger stress of the PPA-CF, it will not have any additional deformation. So in this test, clearly the winner is PPS-CF. Temperature test in the oven. M10 not as a small load. And I'm recording the temperature of the first noticeable deformation. And we can see another weak point of the PLA. It will start to deform at 50-55 degrees Celsius. PETG at 65-70, ABS-ASA around 90. Now in the percentage, these numbers are quite close to each other. And reason for this is that a few companies solved that, I think it's crystallization during the printing, and instead of the 50-55 degrees Celsius, it will start to deform far above 100 degrees Celsius. And this completely deformed my statistics in percentage. Another conclusion is that the fibers always helps. Here we can see 3 examples. In some cases, the annealing can help, for example, with the PET-CF and PA-CF. In this case, we can increase this temperature resistance. This data is all without annealing. Theoretically, we can anneal PLA too, but it will deform, shrink, and warp during this process. And if we need dimensionally accurate objects, it will be completely useless. I have several videos about this. The fibers will reduce this shrinking and deforming. Between PPA and PPS-CF, the PPS is better, but in both cases, these temperatures are above possibilities of my equipment, so this data is from the TDS. Before conclusions, one more time thanks to the Polymaker for sponsoring my channel and to all my Patreon supporters. About these materials, well, don't forget that here I covered mostly mechanical properties, but there is so much more. For example, PLA, still easiest for printing. PETG, a technical filament which is also printable on open printer. ASA, UV resistant material. PPS, one of the most chemical resistant filaments. And there are some filament types which are not covered in this video, like polypropylene. I tested only 2 types so far, and I have 4 more. And looks like it is very fatigue resistant material, resistant to repeated stress. TPU, it is flexible material, and depend of the hardness, the harder materials are very resistant too. PIBA, a new filament type, and looks like it is more elastic compared to the TPU, and for example it is better for those LS basketballs. But is it also very resistant too, like TPU? I'm not sure, but I will test this soon. And if you follow my channel, then we can do this together. Thank you for watching this video to the end, and as always, happy printing!